Okay, some of the more complicated equilibrium questions will require you to use both translational and rotational equilibrium. This question, for example, suppose we have a 75 kilogram mass here hanging from the end of this 10 kilogram pole. So those two will obviously have weight. So there's two forces of gravity pulling downwards, Fg1 and Fg2. Each of those forces create a torque on the pole, wanting to rotate it in the clockwise direction. And those torques are being supported by the tension here in this cable or rope, whatever it is. And let's suppose that it makes an angle here of 50 degrees with the wall. So the perpendicular component of this tension is obviously the component that we're interested in, because that's the component that contributes to the torque. This component here, the parallel component, doesn't. It just pulls the pole into the wall. So this angle would be 40 degrees. This is a right angle, obviously. And so we have torque being created by the tension in the counterclockwise direction, and torque being created by the two weights in the clockwise direction. And we want to know, what is the magnitude of the tension in this rope? Well, again, we know that for this type of question, the torques have to be equal to each other. So in the clockwise direction, I have two torques. The first one is my 75 kilogram mass that is acting at the end of this object, the pole, and we're not told the length of it, so I'm just going to put in L for the length. And then I have a 10 kilogram mass that's acting at the center of mass, so it's acting at half the length. And those two are being supported by the force of tension, but only the perpendicular component. So I'm going to add in Ft times sine of 50. And again, that tension force acts halfway along the length. And now you'll see that the length appears in every term, so we can cancel, divide through by the length. And now the only unknown is the force of tension. So once I put all of this into my calculator, I find that the tension force is 2,439 newtons. Okay. So far we've only used rotational equilibrium. At the beginning of the video I said we would use both. Well, we know that this system is in equilibrium, so we've used rotational equilibrium to find the tension. If it's in equilibrium, then all of the forces should also add up to be 0. And while that might be true in the y direction, right now we only have one force in the x direction, so it's the parallel force of the tension. So there must be another force equal but opposite to this one, and that's the force exerted outwards by the wall. I'm going to call that Fx. So the wall is also exerting a force, right? This rope is pulling the pole into the wall, so there is an equal but opposite force outwards. Now the wall might also be exerting a force up or down. Okay, this pole might be trying to twist a little bit, so there could be a wall force in the y direction as well. So that the force exerted by the wall, it would be this vector here. So how do I find those components? Well, I already know that the x component is equal to the parallel component of tension, which is going to be the tension force times cosine of 40. So 2,439 newtons. And we're going to multiply that by cosine of 40 to get 1,869 newtons. So that is the x component of this force. And again, in the y direction, all of the forces in the y direction have to be equal to 0. So right now I have two forces acting down and two possible forces acting upwards. So I know that the forces acting up have to be equal to the forces acting downwards. Fg2. So Fy is going to be equal to the two weights minus the perpendicular component of the tension. So the two weights, obviously, we have the 75 kilograms times 9.8 plus the 10 kilograms times 9.8, and then we're going to subtract the y component, so 2,439 times sine of 40. And we get a y component that is 735 newtons. So now that we have our two components, the x and the y component, we could solve for the force exerted by the wall. Okay? I'm just going to clear the screen here so we have a little bit more room to write. So the force exerted by the wall is going to be the square root of those two components squared. So the x component was the 1,869 newtons, and the y component 735 newtons. So the force exerted by the wall is 2,008 newtons. And again, we also want to know the angle that that force is acting at. So opposite side will be the y component over the x component, and that force is therefore acting at an angle of 21.5 degrees. So the force exerted by the wall is 2,000 newtons at 22 degrees above the horizontal. And that's how we're going to use both rotational and translational equilibrium in one question. Obviously there's lots of different kinds. This pole doesn't have to be horizontal. It can be at an angle, which is going to make each term have an extra cosine or sine theta, make things a little bit more difficult, but really it's just more button pushing on your calculator. Okay, let's try out some of the questions from the textbook and let me know if you have any problems.